Hello, everyone. My name is Edward. I'm a Master's of Science candidate at Polytechnica University of Bucharest. And in the past several months, I've been working at a new collections framework for the standard library. So I would like to start my presentation by asking you a couple of questions. So first, do you like speed? Yeah, I mean, of course, right? You remember Scott's talk, right? Speed matters. So how about safety? Yeah, I mean, Walter's talk, I mean, they all fallen into place. So that was good, that was great. I felt good about it. And it wasn't like staged. OK, so any functional programmers around here? So you like functional programming. So const and immutable, they are requirements for functional programming, right? You like those. So I don't know if some of you out there know this or not, but the current containers in the STD, in Phobos, they don't support type qualifiers. So it's kind of a shame. I mean, we gave you a couple of great tools. They're fantastic, and then we kind of took them away. So we're aiming to take care of that. So I got a hunch that after this conference, we're going to get a lot of new users. And new users are going to discover ranges, and ranges are great, and they are going to discover the range API, right? And so where I'm pointing to here is that we would like the containers, the collections, to be compatible with the range API, because Scott's talk, consistency, right? I mean, consistency is important. So then, deriving from the range API, it means that we're going to be able to integrate with the existing algorithms in Phobos out of the box. Is that something that might interest you? Right? Thank you. So, not convinced? What's the problem with this? Sorry, it's because of the zoom, but I know it's a bit fuzzy, but like, so let me give you a hint. So we're going to have a dangling range here. So this is a bit of a problem, right? I mean, we wouldn't want this to be able to do so. What if I was to tell you that the design that we approached is going to solve this problem? And that design is that collections are actually ranges plus optional primitives. That's deep, right? I'm going to let it sink in. OK, so collections are ranges plus optional primitives. So our mantra, sort of speaking, is that there are no collections, only ranges. So we're going to have the no GC. We want them to be no GC. Can I hear a yay or not? OK, so and we want to own memory management. So we want the new collections to make their own memory management. So those two, they are kind of related with speed, right? They work hand in hand. Safe, as I previously stated, and we want type qualifiers. We want the collections to be qualified. And during the design and implementation phase, one thing that I constantly kept at the back of my head was that when in doubt, do what int slice does. Again, consistency. We got users to learn about slices, how they can use them, and then we want them to be comfortable with the collections. We don't want to bring a change in behavior. OK, so let's take them part by part, no GC. So it would make sense to be able to create your new list with your allocator, right? So I was pleased to hear all of you in the past couple of days talking about how you like or don't like the GC, or how you like the allocators in STD experimental. We have some pretty cool allocators there, right? The region was mentioned earlier today, I think. So you've defined your great allocator, and you want to be able to use it with the list. And that's something that we should support, and that's something that we do support in the implementation. So I'm going to start off by saying that the allocator is not part of the type. So the allocator is going to be supplied to the new collection. And we are going to support two interfaces, the iAllocator and the iShared allocator. So for the moment, just keep this idea in mind, right? We're going to support those two interfaces, allocator and iShared allocator, and then going to come back later to discuss more detail about why we need both of them and why we require them. As I said, nothing was done just because we wanted, but because we had a reason. So the default, if we don't provide an allocator, we are going to default to either the thread local deallocator or to the shared process allocator, right? OK. Memory management. So for this, we are going to use reference counting. So I would expect that some of you have been either present or you've watched the last year DConference, and I would also expect that you've watched Andrei's talk from last year. So confession time, I stole this from Andrei. Right? OK, so the idea was that when having to deal with qualified types, how do you do reference counting for those types? Because you don't want the reference count to be sealed in. So then we're going to use affix allocator from the experimental module, which is able to allocate an object. And in the front of this object is going to store some extra space for the reference count in our case. And this reference count, this is independently typed from the payload. So for an immutable instance, the payload is going to be typed as immutable, but the reference count not. It's going to be shared. So this, the things are starting to come together. Safety. It's to be expected that if you are going to build a collection out of a safe type, I mean, you're going to have a safe type contained within it, the whole thing should be safe, right? Right? OK. So we should infer it from the contained type. Memory allocation, that should be a safe operation. I mean, what's unsafe from asking the allocator, hey, could you provide me with some memory? I want to create a new object. That should be something safe. The allocation, on the other hand, it's not safe by definition, because the allocator cannot know if the memory zone he is going to deallocate didn't contain any other references to it. But because we have reference counting, we are safe here as well, because we know there are no more references to our buffer. So that's good. That's good. So const and immutable, right? Qualifiers. So as you know, immutable implies that the object is also shareable, right? After you've built your object, it's sealed as immutable, so you are free to share it among threads. Const, on the other hand, he's kind of like the spoiled child. He gives us problems, because const can come from either a mutable or an immutable object. So you don't have any guarantees. Thus, we'll chose to take the more restrictive approach and assume that it's also shared. So let's come back now to the two interfaces, the two allocator interfaces. So let's assume we have an allocator that comes from an iAllocator interface, right? The iAllocator interface doesn't give you any guarantees of how it is able to allocate memory. So underlying, we might have an allocator that it's shareable among threads. But on the other hand, we might have an allocator that it's not shareable among threads. So in this case right here, so assume we have a collection on thread number 1 that wants to allocate a new object for a node in the list. And then on the second thread here, someone calls at the exact same time the allocator. And this is not shareable among threads. So we have a problem. And that's why we need a shared interface allocator, which constricts the allocators to provide shareable methods and means of access, right? So the iShared allocator is going to give us a guarantee that, hey, if I know how to allocate memory, I mean, that's what you would expect from an allocator, then I'm also capable of doing it in a thread-safe manner. So that's really important, and it helps us. OK, coming back to consistency, right? Remember, do what InSlice does. So if you have an immutable slice, you are able to create a mutable copy of the objects there, right? So the collections shouldn't be any different from this. So this code would be expected to work. You should be able to return a mutable copy of our list. Now, the problem is that when we stored the reference to the allocator in the collection, when creating an immutable collection, that allocator became sealed as immutable as well. So when you want to duplicate this list, you actually want a mutable allocator in an immutable collection. So that's kind of a problem. So the next thing we need to solve is, how can we store a mutable allocator in an immutable collection? Any suggestions? Exactly, right? Affix allocator. Again, to the rescue. Da-da-da-da-na. All right, so the way to do it. We're going to use an irreverse allocator. So it's a reference to the snake eating its own tail, right? So how this works is, we're going to have the allocator allocate a piece of memory that's, so the support here is not going to be used. We're just going to allocate 1 byte of memory just because we want actually to get this prefix that's independently typed. And the prefix is going to store the allocator object. And now we can use this allocator and access it. And this must be reference counted as well, right? So all of those have brought together this guy, a mutable T. So mutable T is a reference counted structure that enables you to have a mutable type in an immutable construct. Again, I would expect that those of you who watched Andrei's talk last year, you would also remember maybe that Andrei didn't like a mutable concept, but he was referring to a mutable concept as in C++, where you cast away everything, right? So first, let me talk about a bit the structure here. So this is how this mutable T looks like. This is its state. So we have that support that's 1 byte long, and it does nothing. And then we have the affix allocator that stores the references to the contained type as well, and the allocator it used. So why Andrei is going to like this mutable, and he does, is because if we had a mutable, so if our mutable T is mutable as well, then accessing the prefix is going to give us also a mutable state. If we come from a const, an immutable, or a shared reference, then the prefix is going to be shared. So now we're not losing the qualifiers. Now we know that, hey, we need to take care into this. This is going to be thread safe, right? It needs to be thread safe. Okay, so another good thing that we've got going here. So let's talk about a bit about the primitives. So as I said, we didn't put anything on the table just because we wanted. Everything had a bottom-up approach. So we implemented the collections, and we implemented the primitives as they were needed, or as they felt like they should be there. They should be consistent with the existing API, right? Do what int slice does. So I mentioned we want to comply with the range API, so we'll need at least to be able to cope with empty front and pop front. Now coming back to the functional programming approach, we have tail. I'm sure tail is not unknown to you folks, right? So if you have a mutable collection, right, if you choose to define your own collection following this framework, then if your collection is mutable, then the module will provide a package level tail that knows how to advance to the next element. If your collection is immutable, then you need to provide the implementation for tail, but only for the immutable types. So you're not stranded there. Insert and remove, operator overloadings, concatenation, appending, incrementing, and a lot more. What made sense? One of the guys that made sense during the development process is unique. You would like to know if you have one or more references to one of your collections, depending on what you want to do. Okay, so the current status is that we have S-list, so singly linked list, dynamic, doubly linked list, array, and hash table. They are implemented, they are working, and they work as the current implementations do. So the hash table does as associative array does. the array, there's this in-slice and std container array. So let's talk a bit about some benchmarking. So the purpose was to prove to you guys that we're not falling above, so we're not slower than the current implementation, right? So here with green, I have the implementation in, I'm using the implementation of std array from the std container module. And with blue, it's my implementation of array. And what I did, it was that I created 2 arrays of those many elements, and then I concatenated the 2 of them. And I measured the time. So you can see that we're doing pretty well with the new implementation. It's faster, it's safer, it's qualified, and it's pretty fast. So that's good, that's good. And then I thought, hey, how about a singly linked list? So before I talk about the chart, funny story here, right? So I did the benchmarking for std array, got good results. I was confident. Yeah, good job, man, good job. I was, I don't know, proud of myself. And then I tested the singly linked list, and it was disastrous. It fell into pieces. It was 4 times slower, I think, than the one in std container. And I couldn't get my hand around it. I mean, what's happening? What did I miss? So after 2 hours of debugging, apparently what I missed was that I forgot to compile it in release mode. So time well spent, right? OK, so here I have three charts, 3 lines. So what I did, I plotted the times for, again, same test as the array. So we have a singly linked list from std or container, that's with red. And then the blue line is the singly linked list from experimental. And those 2 folks, they use the GC. So remember when I said that if you don't provide any allocator, then we are going to default to the thread local one, the allocator, which is the GC, right? And for the green line, I used the mallocator. And you can see that we have now a performance increase when we chose our own allocator. And my guess is that this performance increase comes from how the reference counting is done. Because of using affix allocator, so the reference counting is an intrusive approach. So we don't have any extra indirections, right? When we get to the object, we have the reference count next to the object. So less indirections, which apparently are visible here in the benchmarking. So what else do we still have to do? First one is to add more collections, right? I mean, everything sounds good. Maybe, I don't know, I hope I hyped some of you. Maybe you want to play around with those, but we need more than 4, right? Another one is to add shared collections. So, and this is debatable. I mean, how we want to make them, how we want to implement it. And I don't know if it was clear or not, but a lot of the things that have been developed, they use design by introspection. So Andrei's talk earlier, it was really important. I mean, design by introspection is really powerful. It allows you to do a lot of great stuff. So we could use introspection to just add shared to how the collections are right now, not necessarily implement some new ones. And also from Andrei's previous talk, we need to figure out about the composition scheme. I mean, you've seen how a composition scheme is, it's good and it's powerful, but if you need to think about it well enough to be sure that you don't open yourself to cases that are not, I don't know, feasible or they don't make sense. And after those are done, profit, right? D-man is happy. So conclusions, we have a new collections framework that is fast, safe, no GC, and qualified. I'm really happy about it. I hope I don't know, increased your interest in it. I hope maybe you are happy as well. Thank you for your time, and I'm ready to answer to your questions.
Yeah, so when you write collection in D, one of the problems you run into is that, say you have an array of T, and a const array of T, as far as the compiler is concerned, is completely different than the const array of const T, right? Because those are two different template instantiations with two different parameters. And so you always have a problem when we try to not qualify the content of the container, but qualify the container itself. Then things like stop working unless you build some scaffolding or what. So have you considered that in the new design collection? And if so, what kind of solution do you have for that problem?
So the question is that const array of T is different than const array of const T, right?
Yes.
Okay, so I haven't thought of it. Yeah, that's interesting. No, I haven't thought of it, so I have to confess this wasn't something I did during the unit testing part, and I wrote a lot of unit tests, probably 800 lines or something. So yeah, I'll have to think about it, and we can take it offline, and maybe we find a solution together.
So this slide says that the new collection framework is no-GC. How did you manage to do that? Because the last time I checked, iAllocator or the methods of iAllocator were not no-GC. So, and if the container takes an iAllocator as constructor argument, how can the container itself be no-GC?
So right now it's no GC de facto because it doesn't actually create garbage, even though it may use the garbage collector as an allocator. It has the free primitive. So de facto is already not a garbage creating artifact. The URE definitely, the whole iShared allocator thing is essentially the first step in categorizing the allocators by, you got to have a no GC allocator interface, which is whenever you allocate is guaranteed to not be liable to create garbage. And that is a very simple addition it's an incremental addition to our interface. So what happens right now, it doesn't create garbage, but it's not at no GC technically, but we're going to make that the URE thing by adding a new interface, iNoGC allocator.
That was actually my question, but I think I figured out a way to fix it. So.
So I think this typing of the affix, it can introduce aliasing between mutable and immutable data. So what are the assumptions on the specifications of the type systems that you're making?
Can you say that again? Sorry.
So what are the assumptions that you're making on the spec of shared? Because this typing of the affix, it can introduce aliasing between mutable and shared data.
How does it do that?
Well, you can have so you can have a container and then get the affix, then you get a mutable.
Get the what?
Get the affix, then you get the mutable extra data. Right?
Okay.
And then you can cast
the affix, the prefix. Okay.
Or prefix. Yeah. Then you can implicitly convert it to const, which every type allows.
Shared does not convert to const. It converts to shared const.
Yes, but it's mutable.
It's shared.
So you have a mutable container.
Okay.
Then first you get the prefix, then you get the mutable reference to the prefix. Then you can convert the original mutable container to const, which happens implicitly, and again get the prefix, and this time it's shared.
First of all that data is private, so it's under the control of the container. Second, we gotta take this offline because it seems like one of those things with pen and paper. I'm confident we're in good shape there, but definitely there might be kinks that we need to look at.
Okay.
So unfortunately, we're going to have to cut the questions short there. Can we get another round of applause for Eduard? So that will end our scheduled speakers for DConf 2017. We do have an hour of lightning talks that are going to happen next with a special quarter-length talk to kick it off. We'll start that at 12:30. So we'll see you back in a couple minutes, everybody.